All right, welcome, ladies and gentlemen, to our study of definite integrals. So today we're going to be looking at some symbology. A new guy that kind of brought his name into the world of calculus. You see his name down there. I'll get to him a little bit later. And really just areas under the curve. That's really what this whole chapter is about. All right, so let's kind of take a look at this. So this is the guy. This is Riemann, and he gets credited as like the guy that kind of figured out these rectangles and finding the areas under the curve, and noting that the limit of these rectangles that you create, the limit of those areas actually ends up being the area under the curve. So he's kind of the guy that you can blame for this part of the study. Okay, so the Riemann sums, this is just the process that we were doing, like our RAM and our RRAM, LRAM, MRAM, that sort of stuff. It's the process of making infinitely many rectangles to estimate the area under a curve, and then obviously using some limits and some calculus to find the actual area under the curve. So using sigma notation, this is kind of what this looks like if you were to just have some sort of function here. Oops. If you were to just have some function between A and B, it doesn't even matter what the function looks like. Okay, between A and B, if we just started making these rectangles that we were doing before, right? If we think about a midpoint rectangle, this sum is, well, this delta x is just this. This is the width of the box, so this is delta x. And the height of the box is figuring out what c value that you're plugging in. So they're right here, this is a c of x, or c of k, I'm sorry, c of k, and plugging that into the function to figure out the height. If you're using RRAM, then it would be the right side of your interval. If you're using MRAM, it would be your midpoint. Whatever this may be. This is just, then the sigma just represents cutting it into, starting at one rectangle and then summing it to all of them. It depends on how wide you want your rectangles, and eventually you can make skinnier and skinnier rectangles to find the actual area. This comes back a little bit later, looking at the limit of this sum and tying it into our definite integral. Okay, so the first theorem that we're going to look at is the existence of a definite integral. And our theorem basically says all continuous functions are integrable. Okay, it's a new word for you, by the way. Integrable means you can take the integrand, or you can integrate it, just like we had differentiable, because you can differentiate it. Okay, that is, if a function f is continuous on an interval from a to b, then its definite integral over a to b exists, which means you can find the area under the curve as long as that curve is continuous. So again, if you have some sort of function and it's continuous from a to b, as this function is, that means you can find this area. It's possible. Okay, some of our, this is just an existence theorem. This says they exist. Okay, and we're getting later and later into the harder stuff as we go through here. All right, so if it's not, by the way, if it's not continuous, so let's say you have this sort of thing between A and B. If you tried to create rectangles in here, the rectangle heights on the left side would start to get, the height would start to go to infinity, and then it would be really hard to find an area under this curve. Okay, so this means the definite integral wouldn't exist here for our stuff right now. All right, so continuity is very important here, just as it was with differentiability. Okay, here's the symbology. Most of you should probably remember this from last year. This is our integral sign, this big S kind of looking thing. And what this is basically saying, as you see down here on the bottom, this is kind of the statement. This is the integral of the function f from a to b. So here, the a represents our lower limit of integration, and our b represents our upper limit of integration. The function in here is called the integrand, And the x is just the variable of integration. We could change it to anything we want. We could have the integral from a to b of f of t, but here we'd have, okay, well, it's just dt. Okay, or we could say the integral from a to b of f of u du. Okay, we just keep going like that. The variable's not important to us. These just have to be the same variables. All right, so what I'm going to note here, though, is where this really comes from. This statement actually is the limit of all of these Riemann sums, of all of these rectangles that you could have created. If you could do infinitely many rectangles, this limit of this sum would end up being the definite integral. And by the way, we're not really getting into this yet, but the reason it's called a definite integral in my mind is because it's defined between 2 points. Later in our study of calculus, we'll get to the point where we look at indefinite integrals where we don't get any points on here. All right, so today, really, I didn't mention this either, but today we're really looking at just basic functions. Kind of, if you recall the end of pre-calculus where we were starting to look at these as just areas and being able to use our area formulas to find any type of definite integrals. That's really what we're looking at today. Okay. By the way, this right here, super, super important, this little piece here. I mean, this is going to show up quite a bit from now until May when we do our AP exam. So it's important that you understand this very, very simple little thing here. Okay, so the area under a curve. So if y equals f of x, so if you have some function that is non-negative and integrable over a closed interval on a to b, then the area under the curve is this integral. So whatever we have. And note the thing that I just said by right here, we haven't talked about this yet. All of our functions that I've been drawing up here in our graph has always been something like this, from a to b, being non-negative. So this function is non-negative between a and b, which means this area here, this integral, is the area. Okay, so this definite integral between a and b, that's the area. But you might be asking, well, what happens if the function is negative? Well, we have a way of dealing with that. And if the function is non-positive, I'm not sure why we use non-negative and non-positive, but we can still find the area by just using the opposite of what we would have gotten, right? So we can say, okay, if you had a function here and okay, now we have from A to B here, all of this area under here, they would have negative heights, right? Because we'd be plugging in a value and finding the height of this rectangle. Well, the height would be negative. So what we just say is, okay, well, this area is actually the opposite. Whatever we got calculations-wise would be the opposite of the actual area. So we just say, okay, well, the area for the non-positive pieces are just going to be the negative of this f of x, or of this integral. And that's when f of x is less than 0. You'll see what I mean here in a couple of examples that I'm going to give us towards the end here. So just kind of bear with me as we go through this. So this kind of comes up to, okay, what if you had a function that looked kind of like this, just like I had before, and you have a positive part and a negative part, and then I have a to b through here. Well, then I have a negative part and a positive part, and if this function is at all symmetric, like a sine function, which is almost kind of looks like, or a cosine function, if you were to add the positive area and the negative area, the area would come out to 0, which doesn't make sense. And we like to find area between the x-axis and the curve. Okay, so it basically comes down to, if you have both positive and negative values, then the value of the integral is the area above the x-axis minus the area below. So we get a very simple statement like this. And sorry, this is a little blurry. I'm not sure what happened there. So if I wanted to find the area between A and B, I would just find the area above the x-axis and subtract the area below the x-axis, because you'd subtract a negative, so it'd be positive. So you'd be basically adding this and adding this. So x-intercepts might be very important for us, right? Because x-intercept tells us where we cross over being positive and negative. So most of our functions, I think, are pretty easy to solve here, but you never know. You might need a calculator here and there. They give us a little itty-bitty theorem here, and this was actually something we dealt with before in the last section. And the theorem is the integral of a constant. So if you have just a constant function, we kind of already knew this already. If we had a constant function here from A to B, and we wanted to find the area, well, that's just the area of a rectangle. Well, an area of a rectangle is just base times height. Well, the height is C, and the base is the distance between B and A, which is defined by B minus A. And that's just the area. And so it's this little itty-bitty theorem that they're going to give us. So if you tried to find the integral of f of x dx, where f of x is actually a constant value, you would just do C times B minus A. It's a very simple formula. Most of you probably wouldn't even need this formula. You could probably figure out that a constant function, do a little sketch, and you notice we did that. I just did this really quickly without even needing this theorem definition here. But basically, if I gave you the function from -3 to 5 of 6 dx, it would basically say, okay, well, sketching-wise, it would be not too hard, right? 6 is up here. From -3 to 5, I'd have a rectangle, and oh, that's super simple because it's just the height of 6 times 5 minus -3. So the area under this curve is, what, 48, if I did my math correctly? See, super simple for constants, and really simple for the functions that we're dealing with today. Okay, so here's a couple examples other than the one I just gave you. Let's just say I said we had the integral from, let's start easy, 0 to 5 of the function 3x dx. Now, what they want you to do in this particular lesson is really kind of graph the function and go from there using your simple area formulas that you actually already know from geometry, algebra 1, pre-algebra, all that sort of stuff. So this function is the function 3x, which looks like this. And I want to go from 0 to 5. And that just means, different color here, that just means I want to find this area. Well, this area kind of looks like a triangle to me, so I'm going to use my triangle formula. So area is 1/2 base times height, which is 1/2. My base is 5. My height is what I get when I plug in 5, and that'd be 15. And I think I get 75 over 2, which is 37.5, I believe. Okay, so that one's super simple. What if I was to do something like this? Let's go from, let's try something a little bit more challenging here. Let's go from -2 to 5 of the function. Let's go, sorry, I should have thought about this before. Let's go x plus 4 in parentheses, by the way. That's very important, parentheses here. Okay, whenever I put parentheses, that's usually pretty important, so you got to pay attention to that. All right, so again, nice linear function, and we can look at the area here between -2 and 5. X plus 4 is going to be here, and something along that line. So I want to find the area in here. And I know you guys did some of this in the previous lesson, but really this lesson is about the symbology of the definite integral using the notation here and being able to represent this notation onto a graph. But then also, again, I'll show you a negative example in a second here. All right, so I hope you guys remember from the last lesson, actually, and even from the previous class, pre-calculus, that this is a trapezoid. And a trapezoid is found, area is 1/2 base times, oops, sorry, not base times height, that's a triangle. It's 1/2 height times base 1 plus base 2. This is your height, the distance between these two numbers, and base 1 and base 2, or base 2, base 1, doesn't matter, because it's just the adding of both of them, or the sum of both of them. So we get 1/2 of, well, the distance between 5 and -2 is 7, which is your height. And then you got to figure out, well, what's B1 and what's B2? Well, B1 is when you plug in 5, so I get 9. And B2 is when I plug in -2, I get 2. So I get 11 times 7, which is 77, over 2, which in this case is, what, 38.5, I believe. Okay, so that one's pretty simple, I believe. Let's try a little bit harder one. Let's try the function -2x plus 4. And let's go from 0 to 4. Now, some of you might be, oops, sorry, don't forget the dx. Some of you might be thinking, well, that doesn't seem too hard. That doesn't seem too hard at all. It's just a nice, simple linear function going from 0 to 4. It's not a big deal. What makes it a big deal for this today's stuff is the fact that we're up here at 4, and this function at positive 4, if you think about finding, if you're trying to graph this function here, at positive 4, what is that? Positive 4 times -2 is -8, plus 4 is -4. Which means we have this function that goes like this. And now we have a positive piece and a negative piece. Which means we need to use basically two different areas. We need the area between 0 and what ends up being 2, and the area from 2 to 4. And since this one is going to be negative, I need to find the difference of the two. The positive version minus the negative version. Now, I gave a kind of a simple version of this question, but it's still one that adds this negative concept to us. Okay, so if I tried to find the area here, the area would be, well, the area of the first piece, which is positive, from 0 to 2, and that again is a triangle, if I could speak correctly here. So it's 1/2 times a base of 2 times a height of 4. And it's going to be minus this other area. And again, it's 1/2 times the base, which is 2. And if you think of the height here, when x is 4, the height is actually -8. Or sorry, -4. My fault. Okay. So then we get, notice here, this is actually the same number. So if we did just the positive versions, then we would just get 0 again, like I was saying earlier. So I get 4 minus -4, which is 8. So the area under this curve is 8. So this would actually equal 8 up here. Okay, I'm just going to mention one or two little things here is, first of all, they will be mentioning something about this. So if you recall, and they will mention the thing that you need. Sorry for my neighbors there being loud. For sine of x, from 0 to pi is just this. And you're going to use this statement, the fact that this is actually 2, and we'll get to the reasons why this is 2 later when we actually figure out how to find the antiderivative of sine. which some of you could probably figure out. But and then how to use this definite integral in a slightly different manner using our antiderivatives. All right, so you just need to know that this area is 2, and you can find all sorts of antiderivatives, or not antiderivatives, areas here and integrals. But I'm going to leave that to you when you get to me tomorrow looking at this particular lesson. And that's actually it for the day. Like I said, most of the functions that you're going to be looking at today are relatively simple, and you'll be finding the areas under the curves. Use your simple area formulas. Don't forget how to find the area of a triangle, a trapezoid, and probably a circle. You probably want to remember your circle formula as well. All right, so there you go. Have a good evening, and I will see you guys Monday.